Hello, my dear students. Welcome back to Fluid Mechanics lecture series. I am your SumamMiss. My channel name is also SumamMiss. You can watch all my lecture videos on my channel. Today, I am going to discuss about the momentum and the fluid flow. You know, in mechanics, the momentum of the fluid particle or any object that is equal to the product of mass into velocity. Momentum equal to mass into velocity. So consider a section of the tapered pipe. So here you can see that the cross-sectional area is increased from the section AB to section CD. So that means the velocity is changed from V1 to V2. And of course, V1 is higher than V2 because of the smaller area. The particles of the fluid stream will possess a momentum, and whenever the velocity of the fluid stream is changed in magnitude or direction, there will be a corresponding change in momentum of the fluid particles. According to Newton's second law of motion, a force is required to produce this change, which will be proportional to the rate at which the change of momentum occurs. The force may be provided by the contact of the fluid and the solid boundary. By Newton's third law, there is an equal and opposite force that is exerted by the fluid on the solid boundary. Such forces are called dynamic forces since they arise due to the motion of this fluid. These dynamic forces additional to the static forces due to pressures in a fluid. So to determine the rate of change of momentum of this fluid, consider this control volume ABCD. We have to assume that the flow is steady and non-uniform flow. So in that condition, the continuity equation is valid. That is mass inflow that is equal to mass outflow. So that means rho1 v1 a1 that is equal to rho2 a2 v2 that is equal to m. So the rate at which the momentum exits at the control volume across this boundary that is equal to m into v2, and the rate at which the momentum enters the control volume that is equal to m into v1. So the rate of change of momentum, so that is equal to this minus this, or m into v2 minus v1. So the rate of change of momentum that is equal to mass flow per unit time into change of velocity, or we can say that it is the increase in momentum per unit time in the direction of motion. Based on Newton's second law of motion, F equal to mass into v2 minus v1. So this force is the resultant force acting on this fluid element in the direction of motion. Now let us discuss about the force on pipe bend. When do you use an elbow or bend in plumbing? Whenever there is a change in the direction of the flow, then we have to use either elbow or pipe bend. Or sometimes if you want to avoid an obstacle like a beam, then instead of drilling through it, we can use a pipe bend. So you can see a pipe network here, and whenever we want to change the flow direction, we can provide an elbow here. When the fluid is in motion, its momentum will change as it passes around this bend due to the change in the flow direction. So when the pipe tapers, then the magnitude of the velocity that is also changes. Therefore, there is an additional force that is acting between the fluid and the pipe. So here you can see a horizontal pipe with a constant cross-sectional area. So in the case of horizontal pipe, line of action of pressure forces are same. Since it is a constant cross-sectional area, then V1 equal to V2. Whereas in the case of bent pipes, the line of action of the pressure forces are different. So we have to resolve this into horizontal and vertical components. So here V1 equal to V2 because there is no change in the cross-sectional area, but the direction of the velocity changes. And the momentum change occurs due to the change in the flow direction. In this case of tapered pipe, since the cross-sectional area at the section 2 is reduced, then V2 is higher than V1. And the flow velocity is also change in direction. Here also line of action of pressure forces are different. So there is an associated change of momentum. So consider the momentum equation for two-dimensional flow along a streamline. This equation F equal to m into V2 minus V1 is derived for one-dimensional flow in a straight line, assuming that incoming and outgoing velocities are in the same direction. The figure shows a two-dimensional problem in which the velocities v1 makes an angle theta with respect to x-axis and v2 makes an angle phi with respect to x-axis. Since v1 is making an angle theta with respect to x-axis, we have to resolve this v1 into component as vx1 and vy1, where vx1 is the horizontal component of v1 and vy1 is the vertical component of the incoming velocity. Similarly, we have to resolve this v2 as vx2 as the horizontal component and vy2 as the vertical component. So since both force and momentum are vector quantities, they can be resolved into components in x and y direction. So Fx and Fy are the component of the resultant force in x and y direction. So which is equal to mass into change of velocity. So Fx means it is the rate of change of momentum of the fluid in x direction. So that is equal to mass per unit time into change of velocity in x direction. So change of velocity in x direction, that is equal to Vx2 minus Vx1. So Fx equal to mass per unit time into Vx2 minus Vx1. So what is Vx2? It is equal to V2 cos phi and Vx1 equal to V1 cos theta. Similarly, Fy equal to rate of change of momentum in y direction. So that is equal to mass per unit time into change of velocity in y direction. So change of velocity in y direction equal to Vy2 minus Vy1. So Vy2 that is equal to V2 sin phi and Vy1 equal to V1 sin theta. Now the resultant force that is equal to root of Fx square plus Fy square. To summarize this position, so this is your control volume. So total force exerted on the fluid in a control volume in a given direction, that is equal to rate of change of momentum of the fluid passing through this control volume in a given direction. Or we can write F equal to mass per unit time into V out minus V in. V out is the outgoing velocity and V in is the incoming velocity. The total force F that is acting on this fluid in a given direction is made up of three components. So that is F1, that is the force exerted by the solid boundary on this fluid, and F2, that is the force due to gravity, and F3, that is the force exerted on the fluid by the fluid outside this control volume. So the total force F that is equal to F1 plus F2 plus F3, that is equal to mass per unit time into V out minus V in. Now the force exerted by the fluid on the solid boundary, which is equal to F1, but it is in the opposite direction, or R we can write R equal to minus F1. We can study this concept in more detail by solving a problem. In this problem, a pipe bend tapers from a diameter of 500 mm at inlet to a diameter of 250 mm at outlet, and it turns the flow through an angle of 45 degree. That means theta equal to 45 degree. And measurement of pressure at the inlet and outlet show that pressure P1 at the inlet is 40 kilonewton per meter square and pressure at the outlet is 23 kilonewton per meter square. And the pipe carries an oil which has a density of 850 kilogram per meter cube. So we have to find out the magnitude and direction of the resultant force. So this is what we have to determine. And the flow rate is also given, and it is also given that the bend is in the horizontal plane. So when the fluid is in motion, its momentum will change as it passes round the bend if the pipe tapers any consequent change in magnitude of its velocity. Considered a tapered pipe between the section 1 and 2. So this is considered as the control volume. So here is the inlet and here is the outlet. So it is given that the bend is in the horizontal plane. So this part we are considering as the horizontal or x-axis, pressure forces P1 and P2 that is acting at the section 1 and 2 respectively. The line of action of these pressure forces are different. Because of this pipe bend, it deflects the flow through an angle of 45 degree. So this angle is 45 degree or theta equal to 45 degree. B1, D1, A1 are the flow velocities and diameter and cross-sectional area at the section 1. P2, D2, A2 are the flow velocity and diameter and cross-sectional area at the section 2. So the given data are density of the oil is given, pressure at the inlet and outlet that is also available, and discharge is given. Since diameter is given, so we can calculate area at the section 1 and at the section 2. Since the continuity equation is valid, we can calculate the velocities v1 that is equal to q by a1 and v2 that is equal to q by a2. So it is asked to determine the magnitude and direction of the resultant force on the bend, and fluid is in motion. So there is a change of momentum and the corresponding force. So this is the schematic sketch. The mass per unit time entering the control volume, that is m equal to rho into q. Rho is given as 850 kg per meter cube and q is given as 0.45 meter cube per second. So mass can be calculated. And based on the Newton's second law, F equal to F1 plus F2 plus F3, that is equal to mass into V out minus V in. So F1 is the force exerted by the solid boundary on the fluid. So F2 is due to gravity force, so that is equal to 0. F3 is the force due to the pressure of the fluid, that is outside the control volume, acting at the section A1 and A2. So this equation can be written as F1 plus F3, that is equal to m into V out minus V in. Since the force and momentum are vector quantities, they can be resolved into components. So we have to resolve these components in x direction as well as in y direction. So F1 plus F3 of x, that is equal to mass into V out minus V in x direction. So that means this is the rate of change of velocity in x direction, and F1 plus F3 of y, that is equal to mass into V out minus V in of y, that is the rate of change of velocity in y direction. The resultant force, that is the force exerted by the fluid, that is equal in magnitude of F1, but it is in the opposite direction, or R equal to minus F1. So Rx equal to minus F1x and Ry, that is equal to minus F1y, which makes an angle phi with respect to x-axis. So we have to determine Rx and Ry and phi, or in other words, we have to determine R and phi, where R equal to root of Rx square plus Ry square. So F1 plus F3 in x direction equal to mass into rate of change of velocity in x direction. So if you are substituting F1x as minus Rx, then we can rewrite this expression as Rx equal to F3x minus mass into the velocity change in x direction. So how will you find out F3x? F3x is the horizontal component of the force which is due to the pressure of the fluid outside the control volume acting at the section 1 and 2 in x direction. The pressure force acting at the section 1, that is equal to P1 into A1, and the component of the pressure force at the section 2, that is equal to P2 cos 45 or P2 cos theta, but both are in the opposite direction. So F3x equal to P1 A1 minus P2 cos theta into A2. V out is the velocity of the outgoing flow and V in is the velocity of the incoming flow in x direction. Incoming velocity, that is equal to V1, so that is in x direction, whereas outgoing velocity is in this direction, so its horizontal component, that is equal to V2 cos 45, it is same direction as that of V1, so V out equal to V2 cos theta and V in equal to V1. So we can substitute here then you will get Rx equal to P1A1 minus P2 cos theta minus mass is replaced by rho into Q into V out equal to V2 cos theta minus V1. Similarly, we can find out Ry. So if we are considering this equation in y direction and substituting Ry as minus F1y, then Ry equal to F3 of y minus mass into the change in velocity in y direction. So F3y is the force due to the pressure of the fluid outside this control volume in y direction. So here there is no component of the pressure force in vertical direction, whereas here the component of the pressure force in the vertical direction, that is equal to P2 sine theta, and it is in the vertical direction. So F3y, that is equal to 0 plus P2 sine theta into A2. Similarly, there is no component of the velocity in y direction at the section 1. So this is equal to 0, and V out, that is equal to, that is V2 sine theta, but it is in the opposite direction. So V out equal to minus V2 sine theta. So if you are substituting Ry equal to P2A2 sine theta minus rho Q into minus V2 sine theta minus 0. So this can be simplified into Ry equal to P2A2 sine theta plus rho Q into V2 sine theta. So the resultant force in x direction is represented by Rx, and it can be calculated by using this expression, and the resultant force in y direction can be calculated by this equation. So all input values are available with us, so we can directly substitute the values in this equation and calculate Rx. So P1 is available, that is the pressure at the inlet. A1, that is also calculated. Theta is 45 degree. Rho is given as 850. So all informations are available. So you can calculate Rx as 5.454 into 10 Qn. N stands for Newton. And Ry, that is equal to P2A2 sine theta plus rho Q V2 sine theta. If you are substituting, you will get Ry as 3.277 into 10 raised to 3 Newton. So resultant force equal to R equal to root of Rx square plus Ry square, which is equal to 6.362 kilonewton, and the direction of action of this resultant force, that is equal to tan inverse of Ry by Rx, so that is 31 degree. So resultant force is equal to 6.362 kilonewton, and line of action of this force, that is equal to 31 degree. So all of you, please go through the problem and work out this problem by your own and verify the answer. It is my request. Similar situations you can see in our household connections and industrial pipe networks. For the time being, it is enough. Thank you for your patient listening. For any queries, please feel free to contact me, or you can comment. Your comments are always welcome. See you. Your SumamMiss.